So again, you've watched the video with most of the definitions about the vectors, but the whole point of this lecture is to do a review of linear algebra. And basically, we'll just go over definitions, how to manipulate vectors and matrices, how to multiply them, and in this lecture, basically, matrix-matrix multiplication will be sort of the most, not problematic, but it takes a little bit of practice. How many of you have seen matrix-matrix multiplications before? So there's maybe a few people where it's completely new. But it's going to come up in multiple classes. Normally it comes up in math class, and here we're trying to just do a speedy review so we can move on. And then also what we already went over in this video was the linear combinations of vectors, dot product of vectors, determining whether two vectors are orthogonal, using vector norms, and so forth. Was there any concept from the video that I should go over again? Dot product is okay? Okay. Determining whether vectors, when are vectors orthogonal? When the dot product is 0. So if scalar, inner, or dot product, there are three names. If it's 0, that basically determines whether vectors are orthogonal in 2 dimensions, in 3 dimensions. Well, in more than 3 dimensions as well. It's just that in more than 3 dimensions, we have trouble visualizing what orthogonality means. But the concept remains, and it can be defined in any number of dimensions. Okay, so I'm going to walk over the slides that were in the video. So I'm just going to go through some other content. So I'm actually going to now talk about motivation. So there's this whole math with matrices and vectors. Well, why do we need it? What's so important? So I was wondering if all of you could come up with some occasions. So we have 1D arrays, which we call vectors. We have multiple dimension arrays, which are matrices. I could have them in any number of dimensions. And I'm wondering if you could come up with some, so linear algebra just overviews the mechanics of how do I work with them and how do I manipulate them. But why, as an engineer, do you need to know about matrices and vectors? Could you come up with certain properties that are stored as vectors and matrices in petroleum engineering or any engineering, or any application? So what do we do when we do petroleum engineering operation? Which survey is the first survey? Seismic survey. Okay? So seismic survey goes in first to figure out, after seismic data is processed, whether it's a good reservoir. Okay? How fractured or faulted it is, and do I have any hydrocarbons which should, as a larger mass, show up on seismic survey. So when I do a seismic survey, a thumper truck goes in, okay, and it's going to basically collect data with geophones. It's going to produce sound waves that are going to reflect back up. Right? And that data is collected either as an aerial data, or even these days 3D, 4D data. Well, the moment you have data that is in multiple dimensions, or single dimension or multiple dimensions, that is collected, those are matrices. Okay? If it's aerial data, that's a matrix of velocities that are typically with that, or the travel times that are there. Post-process, you get the velocity. So essentially, that's one example. So now that I gave you one example, can you try more? You had that class introduction to petroleum engineering. You went over certain data sets like that. You're looking at something here. This is a one of the well logs. It's not the most common one, but it's the only obvious example in this room. Okay. So this looks like a UPI ultrasonic Warhol telehumor image. So this is an image. The moment it's an image, I'll actually have a pixel for every spot around the well bore. So let's say that I have any image, it's going to be an array, two-dimensional array of what we see as colors, but color is just an interpretation of numbers underneath. So then basically in that two-dimensional array, I have a number for every position, and that is a matrix. There are much more common logs that are basically just arrays of data that are vectors. So I will, for instance, have a porosity log. So I will have porosity for every depth. So I drill a well, okay, and I have a porosity for every depth, for instance. That's a vector, okay? So any other well log like that, traditional well log, will be a vector. It might be resistivity data, it might be porosity data, it might be any other data that I might interpret from it, and it's a vector of data. So vectors, and these are actually large vectors, and we're going to have one of the EKI exercises in this course. We'll be taking a well log and actually just reading it in and manipulating it, and everybody gets upset because there's like actually 14 different logs. So there's like 14 different columns in a matrix, and each of them is one of these well logs. So there's plenty of arrays, and these arrays get like unwieldy and large. So basically, and you could also have them in time. Any other data that you might want to measure, so let's say that you're measuring temperature somewhere, even if it's a gauge in your house. If you log that data every morning at 7 a.m. and you have certain temperature gauge outside, right, you will get time series, which is essentially a vector of data that you need to process. So basically, all of the data is stored in matrices and arrays, though when you're practicing linear algebra and you're doing these 3x3 matrices with numbers like 2, 5, and 7, 1, 2, and 3, it gets hard to picture that actually all of the data that we work with in real life, in any field, is actually comes in those arrays. Because the ones that you play with in class kind of look small and funny and not useful at all. Okay? Very useful. So linear algebra shows up everywhere. And manipulation of matrices and arrays is basically the foundation for processing. So this is, well, we didn't work in pairs, I was actually talking. So we figured out what are the examples of petroleum engineers. Now, why is the vector norms? There was an issue vector norm, and there was an L1 norm, an L infinity norm, and an L2 norm. So there are all these different norms. And so norms help us compare things. So here's one day-to-day Austin thing where norms can be helpful. Okay? You typically have to compare things and you have to make a decision. That's the most common basis for needing a norm or any kind of measurement. So for instance, stage 2 watering restrictions are activated in Austin when combined storage levels of Lake Travis and Buchanan drop below 900,000 acre feet. So that if I was actually collecting the data, and LCRA, which is Lower Colorado River Authority, does that, and you can actually monitor that data online. So if I was figuring out like how to set up an alert for this stage 2 watering restrictions, there's actually a little computer program figuring it out whether that alert should go off, and then email is sent to an appropriate engineer, and then that sets motion for stage 2 watering restriction, I'm presuming, something like that. Basically, I will take both lakes, sum up their volumes in acre feet, and figure out the norm of it, or a threshold. So if my sum is larger than or smaller than, do something. Okay? So if I drop below 900,000 acre feet, I will set up an alert. Which norm is that? If I have a small vector, 2 entries, one of them is storage level for Lake Travis. The other one is storage level for Lake Buchanan. It's L1 norm. Okay. So in this case, L1 is useful. If I was just measuring a distance to somewhere, okay, which norm would I use? L2. So if I'm a little Google map, okay, and I'm trying to figure out number of distances and what is the, so basically the Google map underneath it has probably computes in real time the distance from one spot to another, okay, and then quickly compares them. So there's this computation of distances, depending whether it's aerial distance or maybe it's snapped to a grid of roads. But come down, ultimately I'm going to have one street and going to point to point, that's going to be a L2 norm for distance, right? Now, there's actually L1 that shows up as a distance as well. It kind of doesn't, initially I'm thinking that distances in L2 are the most intuitive things because we're used to Euclidean distance world, okay? But L1 is actually a distance, a physical distance as well. If you imagine that you're actually what's called on a Manhattan grid, okay, and you're snapped to a coordinate system. So distance between this point and this point, Euclidean distance is green, right? What's an actual distance? That's how I gotta go around buildings to get there. So my actual distance is actually L1 norm. Because when I think about it, I have how many horizontal segments? 1, 2, 3, 4, 5, 6. Plus how many vertical? 2, 3, 4, 5, 6. So it's 6 plus 6. So my distance is actually 12 from this point to that point if I'm on this type of a grid. So sometimes L1 is a distance. My point is it's relative. And sometimes one is more useful than the other. You also have L infinity norm. Okay. So sometimes all I'm interested in is in a maximum value. Okay. And that could be a norm in itself. If my worst case scenario is larger than this or larger than that, right, then something might be. So in certain situations, L infinity norm or maximum norm might be more useful. So again, it's up to you to decide which one is useful. And this is more sort of a lot of words for you to refer to later. Sometimes it's also important to know if I have a lot of data, and let's say that I have logging data or any kind of stream of measurements, there are bound to be errors in those measurements. And those errors, if I'm looking at the norm that is kind of summing up everything up, different norms will take those errors into account differently. So for instance, L infinity norm is very sensitive because if I have one error large measurement, it's suddenly going to be an outlier that is going to take the stage and take everything else out of consideration. So that's maybe not the best norm unless I filter data before. Okay. If I take L2 norm, that very large value or very small value is going to be squared, summed up with the other and taken the square root of. Versus if I had L1 norm, it's just going to be taken as a value. So in that sense, small entries in a vector, they sort of contribute more to one norm than they do to the L2 norm because of that. So essentially, I might want to be sensitive to that if I know that my data is nice. Point is, you have choices, and sometimes you actually have to spend a little more time thinking and comparing which one works for your situation best. You have large, similar thing, large entries in a vector, they will contribute more to the 2 norm because I will square them up and they will kind of take over the sum and then I take square root of that. So, depending on the situation I might do it. And now a little bit of fun. Okay? So if I'm in my standard L2 norm, which is Euclidean distances that you're used to, then the first picture is a picture of a circle. And circle of this radius 1 is defined, we know, as x squared plus y squared is equal to 1. That is the circle with respect to the Euclidean norm, or distances that are based in Euclidean. Now, if I had actually, if my world was through L1 norm glasses, circle would look like which one of these? Does the second picture look like a circle to you? But it actually is an L1 norm. So this is world skewed through glasses of L1 norm. So the definition of a circle is that square root of x squared plus y squared is equal to 1, correct? So my L2 norm of a vector is 1. If my definition of a circle is that L1 norm of a vector is equal to 1, not L2, but L1, then I don't have that square root of x squared plus y squared is equal to 1 anymore. I have absolute value of x plus absolute value of y is equal to 1, correct? Okay. Now let's walk around this circle. So if I take this mouse visible? Yes. This point, this is point 1, 0, right? Its norm, L1 norm is 1. Its absolute value of 1 plus absolute value of 0. Right? If I walk now to the point here, okay, let's say it's 1/2, 1/2, right? Absolute value of 1/2 plus absolute value of 1/2 is 1. Is this point that I'm pointing at on the circle in L1 norm? Yes, it is. And actually, that's true for everyone. This is probably 2/3, 1/3. Okay. Its L1 norm is 1. This is 1/3, 2/3. Its L1 norm is 1. So all of these points here on this line are on the circle in L1. If I'm looking at the circle through L1 norm, or distances defined by L1 norm. Same thing for all of these lines, same thing for all of these lines. Here I have minus 1/2 minus 1/2. Its L1 norm is 1. Absolute value of minus 1/2 and plus absolute value of minus 1/2. So this is how circle looks like in L1 norm. And this is how circle looks like in L infinity norm. So for all of these points here, right, their maximum value between their x and y is 1, right? That means that their L infinity norm is 1. For all of these points here, the maximum coordinate is 1, because they're actually on a line where x coordinate is 1, right? This line here. Same thing here. The moment I'm here, my maximum coordinate becomes larger than 1 because it's actually the -2 or something like that, right? So I'm out of the circle. So this is basically the lines, how circles look like in different norms. Because actually the original definition or the more encompassing definition of a circle is that when I say square root of x squared plus y squared, it's actually L2 distance. All right. So now I'm gonna, instead of switching, we're gonna do another video on the material. I want you to actually start working on your homework. Okay? So take a piece of paper. And the homework was posted, I hope. Oh, it wasn't posted. Interesting. Okay. take. Okay. It's going to get posted online a little later. But part 1 of the homework, matrix and vectors operations, will be as follows. So take alpha is equal to 4, beta is equal to minus 2. And these are definitions of x, y, u, v, w. So for this first part of vector operations, which I want you to start working on and hopefully complete today, is this first problem. So you will have to basically complete alpha y plus beta x, alpha u plus beta v, and so forth. Sure. Let me actually, I'm going to download it. Oh, it didn't download. Just a second. Oh. Is this good? If not, I'll open it.
So these homeworks, you turn them in like later?
Yes, but you're going to now start to get going. And hopefully you'll have number 1 solved, so that will be out of the way. I'll stop the video because